This is Myrick Marsh. Over millions of years, the organisms in this marsh will die and become buried in sediment. Eventually, when subjected to immense heat and pressure, the organic material may turn into substances like coal, oil, and natural gas. These are examples of fossil fuels. Fossil fuels are made up of hydrocarbons, compounds containing only the elements hydrogen and carbon. When fossil fuels are burned, the hydrocarbons are oxidized, releasing the greenhouse gases carbon dioxide and water vapor into the atmosphere, which contribute to global warming. But what if we could reverse this process by using carbon dioxide to synthesize hydrocarbons and close the carbon cycle? This is the overall reaction for the reduction of carbon dioxide into hydrocarbons. Note that it is the opposite of the combustion reaction. This reaction forms a number of carbon compounds as products, including carbon monoxide, methane, and ethylene. Carbon monoxide is an important intermediate for this reaction. Carbon dioxide is first converted to carbon monoxide before converting to other products. However, not all the carbon monoxide is converted, so some of it shows up among the overall products. Methane and ethylene are the two main products of this reaction. Methane is the primary component of natural gas, which is used for heating and electricity generation. Ethylene is derived from petroleum and natural gas and is used to make polyethylene, which is the most widely used plastic in the world and is found in things like plastic bags. To get a better understanding of the reaction mechanism, let's take a closer look at the reaction to produce ethylene. The reaction happens in two parts: the oxygen evolution reaction, in which water is split to form oxygen, protons, and electrons, and the carbon reduction reaction, in which carbon dioxide combines with protons and electrons to form hydrocarbons and water. These two reactions sum to the overall reaction. The whole process occurs inside of an electrochemical cell. The electrochemical cell consists of an anode, the electrode where oxidation occurs, a cathode, the electrode where reduction occurs, an electrolyte solution between the two electrodes that dissolves the protons, electrons, and other products, and an ion exchange membrane which separates the two halves of the electrochemical cell, preventing reduction products from moving to the anode and being oxidized, but allowing free movement of protons and electrons. An electric current is applied to the anode to split the water, releasing protons and electrons as well as oxygen gas. The protons and electrons are then used to reduce carbon dioxide into hydrocarbons. We can see here that we have water as the reactant at the anode, and oxygen is created as the product at the anode. Carbon dioxide is the reactant at the cathode, producing hydrocarbons as the product at the cathode. The protons and electrons are intermediates in this reaction. One of the problems with this process is that the carbon reduction reaction occurs very slowly. To solve this issue, copper is used as the cathode to catalyze the reaction. The copper catalyst works by adsorbing the carbon dioxide molecules from the electrolyte solution onto its surface. This weakens the carbon-oxygen double bond, allowing the carbon dioxide to be reduced to form carbon-oxygen single bonds, carbon-hydrogen bonds, and carbon-carbon bonds. These intermediate products then combine and desorb from the copper electrode back into the electrolyte solution, forming the final products of the reaction. This reaction occurs without high temperature or pressure. When combined with a renewable energy source, such as solar power, for electricity generation in the synthesis of hydrocarbons and the products derived from the hydrocarbons, it can effectively reduce reliance on fossil fuels and help remove carbon dioxide from the atmosphere.